This is the second part of the equilibrium expression notes. We are going to focus on writing these KEQ or equilibrium expressions and doing calculations in this part of the notes. As we start to look at how we can use those KEQ expressions in order to look at solving some examples, we're going to be looking at writing out our reactions and the KEQ expressions and then doing some calculations with that expression that we get. So writing out that equation, we've got solid carbon, and it is going to react with oxygen gas, oxygen's diatomic, to produce carbon monoxide gas. So we need to balance. So I need 2 oxygens here, so 2 here. As I now look at this, writing that KEQ expression, our KEQ, we write the concentration of our products over the concentration of our reactants. Remember that the square brackets represent concentration. So these here, concentration of our reactants, concentration of our products. And we're only going to include things whose concentrations can change. So something like a solid can't change concentration, but gases and aqueous solutions can. So I'm not going to actually include carbon in my equilibrium expression. So now as I write that equilibrium expression, I've got KEQ, and that's going to be concentration of my products. In this case, we only have one product. So we have got concentration of carbon monoxide, and anything that was a coefficient for balancing is going to become an exponent to account for the 2 moles that we have. And then that's our only product that we have over our reactants, concentration of our reactants. So concentration of O2, this has a exponent of 1, or a coefficient of 1, so there's a 1 there. And this is our final KEQ expression. So how can we use this? Well, determine the value of KEQ if the oxygen concentration is 0.0144 molar and the carbon monoxide concentration is 0.0027 molar at equilibrium. Well, now we know, and again, those square brackets mean concentration of. Well, that concentration of oxygen, we can plug that in. That concentration of carbon monoxide, we can plug that in. And now we're able to figure out what is the value of KEQ. We've got our carbon monoxide, we've got that 0.0027 squared all over that 0.014, and then we can go to our calculator and plug that in. And so we end up with 0.000. I'm going to do 2 sig figs, 5,2. That's our KEQ value. KEQ, that is just a ratio of those concentrations, so there are no units on our K values. And so we don't need a unit written after that number. And what does that K value tell us? Well, what side is favored in or at equilibrium? Well, 0.00052, that value is less than 1, which means that I'm dividing by a number that's larger. So we have that larger concentration in our reactants, so those reactants are going to be favored with that. So because that KEQ value, and we're always comparing it, is it equal to 1, less than 1, greater than 1? Because that KEQ is less than 1, that means that the reactants are going to be favored when we are at equilibrium. All right, let's go to another example. If you want, pause the video, write out the equation and the KEQ expression on your own. Hydrogen gas, hydrogen's diatomic, reacts with iodine gas, and we do need, iodine's also diatomic, we do need to include the states of matter because we need to be able to identify what is going to change concentration to produce gaseous hydrogen iodide. And because this is they are equilibrium reversible reactions. We should have that double-sided arrow. I forgot to do that right away on this one. So a double-sided arrow there. And so reversible reaction, double-sided arrow, to produce gaseous hydrogen iodide. So we've got hydrogen's a +1, iodine's a -1. So HI, and that is a gas. As we look at balancing, I need a 2 here. And so there is my balanced equation or reaction. Now writing that KEQ expression, remember we're only going to include things whose concentration can change. All three of these are gaseous, and so that they all can change concentration. So then as we do, writing our KEQ value or expression, and it's concentration of products over concentration of reactants, we've got our products, our HI. So concentration of HI, there's the coefficient of 2 is going to become an exponent. That's our only product, all over concentration of reactants, concentration of hydrogen, concentration of iodine. Each reactant is going to, or each chemical is going to have its own concentration. So those go in separate brackets, and those are multiplied together if we kind of look at the denominator there. So determine the KEQ value if hydrogen's concentration is 0.016 and iodine's is 0.025 and HI is 0.0065 molar at equilibrium. We can go ahead and plug those in. So that KEQ, we've got HI, that's going to go on the top there, and we'll have that HI squared over our H2 hydrogen times that iodine. So we've got that 0.016 times 0.025. And then we can plug that into our calculator, and I get 0.11. So our KEQ, 2 sig figs, because all of those have 2 sig figs, our KEQ value is 0.11. Again, that does not have units on it, but that's a ratio telling us what is favored. So what side of our reaction is favored at equilibrium? Well, our KEQ value is less than 1. We're comparing it to 1. And so again, our reactants are favored, because to get a number less than 1, it means that whatever's in the denominator, there's more of, and that is our reactants. So reactants are favored at equilibrium with those concentrations, meaning we would see a higher concentration of hydrogen and iodine gas when we are at equilibrium than that HI. If we wanted to model this, I didn't put any modeling on this section of notes, but we could go ahead and model that, and showing that the reactants are favored, we could go ahead and show now my reactants are hydrogen. So I'm going to have that H2, oops. So H2, I2, we have a lot of those, but we are going to have not a lot of that HI, but we do have 2 moles of that HI. So you could show it with those being smaller and these being larger. We could also kind of break this up and say, here are my products, here are my reactants. And I have more reactants than products in my sample at equilibrium. All right, number 3, nitrogen dioxide gas decomposed to produce gaseous nitrogen tetroxide. So we've got nitrogen dioxide, so NO2 gas decomposes to produce dinitrogen, so N2O4 gas. So with this one, this is a little funky. We've got a 2 in front here. Again, that double-sided arrow, as we have a reversible reaction. You could do that double-sided arrow. You could do 2 arrows going opposite ways, 2 half arrows. Any of those are fine. And then this 2 in front to balance. Writing our KEQ expression, we need to make sure we're only including things whose concentrations can change. So both of these are gases, so both will be in there. We don't have to exclude anything from our KEQ expression. And KEQ, that is the concentration of our products to our reactants. And so our product N2O4 concentration on the top, you need those square brackets because that is, we are looking at that concentration over our NO2. That NO2 though is, we have 2 moles of it, so that is squared. Determine the KEQ value if you have a 4-liter container with 0.075 moles of NO2 and 0.015 moles of N2O4. Well, concentrations, molarity, is moles per liter. And so with this, we do need to figure out, okay, what is the concentration of each of those? So that concentration, moles per liter, let's find, well, what is our concentration of NO2? If we have 0.075 moles of NO2 in a 4-liter container, then we can find that concentration to be 0.01875 molar. I'm not going to do sig figs on that yet. I'll do sig figs at the very end. But now I know the concentration of that NO2. I can also find, well, what is the concentration of my other gas? Doing the same thing. They're in the same container. So then we're looking at, well, what is the concentration of our N2O4? Well, moles per liter, we have 0.015 moles of N2O4 in that 4-liter container. And so then we can find that concentration, which is 0.00375 molar. And that's what we can plug in for that concentration at the top. So we might have to find concentrations. We know how to find concentration in terms of molarity from our solutions unit, and gases do count as solutions. And then we can go and plug those in. So that KEQ, we're going to have the concentration of that 0.00375 divided by the concentration of our NO2, and then that one though does get squared. So KEQ, we can go ahead and do that calculation. This divided by 0.01875 squared, we get the value of, I got 10.6 repeating. Looking at now my sig figs, let me go back to my values. 4.0 is 2 sig figs, 2 sig figs, 2 sig figs. So this would be a KEQ value of 11. What does that indicate? What side of the reaction is favored at equilibrium? Well, if our KEQ is greater than 1, that means whatever is in the numerator, products, is favored. And so that would be products favored at equilibrium. If we wanted to model this, there's my 4-liter container, and I can go ahead and model this. My products are going to be favored, so that means that I'm going to have more of that N2O4, and then I'm going to have less of that NO2, but I do have 2 moles of that NO2. So showing we have, that's going to be taking up more space. You could also kind of separate that out, and instead of saying the chemicals, we could say our products and reactants, just to show which one is favored, meaning there is going to be a higher concentration of that at equilibrium. Reach out to your teacher with any questions.